Okay, so this is starting a brief, just really 2-day overview of acids and bases. And you probably have learned something about acids and bases before in middle school or biology. Usually, when we first start talking about acids and bases, we talk about the properties that they have, sort of their physical properties and maybe some chemical properties, but not so much about the actual chemical makeup of acids. So again, acids, you probably learned this before, have a sour taste. Think of like citrus fruits. We know have a lot of acid in them. They react with many metals. We saw that, if you remember back when we looked at the activity series, and acids turn blue litmus paper red. And some common acids, you know it's an acid because it will end with the word acid, but hydrochloric acid, sulfuric acid, nitric acid, some of these are more common in like food components. So example, acetic acid is the active ingredient in vinegar. Carbonic acid is what makes carbonated beverages. Carbonic acid is what happens when carbon dioxide dissolves in water. It reacts to form carbonic acid. And bases, similarly, you may have learned some of their properties too in middle school. So bases have a bitter taste. Not a lot of food that we have has bases in it. So that taste that it's hard for me to give you a food that like, oh, it tastes bitter because it's made of because it's made of a base. But one thing that bases definitely do is they feel slippery like soap, and that's because bases are a component of soap, and bases turn litmus paper blue. And so we can remember bases and blue go together. So then we know acids turn litmus paper red, bases turn litmus paper blue, bases blue. And then so some common bases, you can notice even without us having a conversation about what is actually made up of bases, you can see that some of these end in the polyatomic ion hydroxide, sodium hydroxide, potassium hydroxide. You can see that they're used in soap production. Sodium bicarbonate is an antacid and it's part of baking soda. It's the source of carbon dioxide that allows baking soda to cause a cake to rise. And then ammonia is a very common base, and it's used in a lot of cleaning products. So you could see soap detergent, that a lot of times bases are used in cleaning products. So what chemically makes an acid and a base a base? And we actually have 3 different definitions. And it's sort of like each time we are going to encompass more substances can become acids and bases. So if you kind of think of it as like a square versus a rectangle versus a parallelogram versus a quadrilateral, that, a square is a type of quadrilateral. Not all quadrilaterals are squares, but all squares are quadrilaterals. It's sort of each time we have a new definition, we get to include more compounds. So this is the tightest definition, the smallest definition. And in an acid dissociates, so that, remember, that means breaks up, to produce the H plus ion in an aqueous solution, and bases dissociate to produce OH minus in an aqueous solution. So look at these examples down here. Here's HCl. You can see HCl begins with a hydrogen ion, and when it dissociates, it produces H plus. Here's NaOH, a base. It ends in the hydroxide ion, and when it dissociates, it increases the OH minus concentration in aqueous solution. Now you may have started to figure out, well, what if I take an OH and I add it to an H plus? That makes water. That's why acids and bases neutralize each other, We're going to talk more about that, but we're going to move on to the second definition of an acid and a base, and that's the Bronsted-Lowry definition. When we talk about a Bronsted-Lowry acid or a Bronsted-Lowry base, we're going to describe an acid as a proton or H plus donor. So now let me revisit that idea. If I think of a hydrogen atom is just one simple proton. There's no neutrons in most hydrogen atoms, and there's an electron that's orbiting it. So now if I have an H plus ion, that means that its electron has been removed. So really, isn't an H plus ion the exact same thing as a proton? And so we will use those two words interchangeably. You can see it right down here, right? Proton, H plus ion. We're going to use those words interchangeably. You may also hear us also use the hydronium ion as a synonym. Basically, this H plus, this proton, is so reactive that if it is in a solution of water, it's actually going to react with that water to form H3O plus. And there's some variations of that. That's showing it, that's maybe a little oversimplified, but that's how we generally describe it, as an H3O plus ion. And so all those things are really synonyms for each other, and therefore an acid is a proton donor. It has to give its hydrogen to something else. We can see it here, giving its hydrogen to water, forming that hydronium ion and leaving the chloride ion as by itself. So therefore, a base is sort of the opposite of that. A base is going to be considered a proton acceptor, right? It doesn't donate, it doesn't give its H, it takes the H from water. Remember, we had a way of writing water as HOH? Well, look at what has happened here. The NH3 has grabbed the hydrogen off of water, leaving NH4 plus, or becoming NH4 plus, and leaving this OH minus. So then we can kind of see how that other definition, the Arrhenius acid and base, sort of makes sense. An Arrhenius base increased OH minus concentration. But then we said, how can ammonia be a base if ammonia doesn't even have an OH? These guys seemed pretty easy to be bases because they have that hydroxide, that OH minus group, but ammonia doesn't even have that. How can ammonia be a base? That's why we knew we needed to broaden our definition of a base, because we know this compound ammonia is definitely a base. It has a pH greater than 7, it turns litmus paper blue, it feels slippery, it has all of the characteristics of a base, so we know we needed to increase our definition. And now another strange thing you may have noticed is going on here. Let me just erase all these. If I look at water in this case and water in this case, what has been going on? Well, here, water accepted the hydrogen. Does that mean that water was acting or was a base there? Seems like it. And remember here, water was what gave NH3 its hydrogen. So it seems like water has acted as an acid there. It's donated its hydrogen. So that may seem weird. That is a very important characteristic of water, that it is something called amphoteric. Amphoteric means it can act as either an acid or a base. And the next slide here has us looking at the specifically, if you look, the second reaction that's going on, that ammonia reaction. Because what is a little different about this is look at the arrow in that. The arrow in that is a forwards and backwards arrow. I'm just going to go back down to this. Notice in this one, the acid definition, that chemical equation was just a forward arrow. This is a forward and reverse arrow. So what the heck does that mean? That means that the reaction can go in both directions and is going in both directions. So NH3, right, can grab a hydrogen ion off of water, and then it will make this. But then look, this is one of our polyatomic ions that we learned. This was the ammonium ion. And the ammonium ion can then go and give one of its H's back to the hydroxide ion. And so this forward reaction is happening and this reverse reaction is happening. In the backwards reaction, what does the ammonium do? Well, it gives a hydrogen, right? It has 4 and then it has 3. So it must have given its hydrogen ion. So what did it do? It acted as an acid. And OH minus acted as a base because it accepted the hydrogen ion. You can see that information is represented up there as well. And down there. And we have labeled them a conjugate acid-base pair. A conjugate acid-base pair, it will only differ by an H+. So how do I know if I have a conjugate acid-base pair? Well, acids will become conjugate bases when what do acids do? When they donate a hydrogen. So when they lose a hydrogen. And then bases become conjugate acids when they gain a hydrogen, right? So that's why they only differ by 1 hydrogen. So you can see here was the base. Here was the base. It became the conjugate acid when it gained a hydrogen. Here's water acting as an acid. It became a conjugate base after it donated its hydrogen. So looking at this example here, we're going to label them as acids and bases on the left and conjugate acids and conjugate bases on the right. And remember, the acids become conjugate bases and vice versa. So which one of these is an acid? So which one of these gives up its hydrogen, right? That's how we know which one of these gives up its hydrogen. Well, over here, this substance has 1 hydrogen. This substance over here has 2. So it hasn't given up a hydrogen, it has gained a hydrogen. Over here, water has 2 hydrogen and hydroxide only has 1. So what seems to have happened to me is that the water is the acid here. And remember, water, or whatever the acid is, becomes the conjugate base, which must mean that this is a polyatomic ion, the hydrogen carbonate ion. This was the base, and it has become the conjugate acid. Remember, conjugate acid-base pairs only differ by a hydrogen. So for each one of these, you should see that they only differ by a hydrogen. Take a second, pause the video, and look at the next example and see if you can figure out which one is the acid, which one is the base, what's the conjugate acid, what's the conjugate base. Again, very similarly here, water is acting as the acid. How do I know that? Because it has 2 hydrogen over here, and it has lost its hydrogen over here. So water has become the hydroxide ion, the conjugate base, which must mean that this substance here was the base, and after it gained a hydrogen, it has become the conjugate acid. The other way is to look backwards. This has an H, here it doesn't have an H. So this guy must have given this guy its hydrogen. So hydrogen ion donors are acids and acceptors are bases. And if we look for this reaction here, or what happens when we add an acid and a base here, this is that neutralization reaction that we've already looked at, right? Here's the acid, right? HCl we know as a strong acid. Here's the hydrogen. KOH is a base. Here's its OH minus. And look at what has happened, right? This is our double replacement reaction where the positive of one has hooked up with the negative of the other, in this case to make water, and the negative of one hooks up with the positive of the other to make this KCl, which is just an ionic compound. And if it's aqueous on both sides, we would even call those spectator ions. And this happens with every acid-base neutralization because every acid is going to have this H plus component. Every base is going to have an OH minus component or produce OH minus when it reacts with water. And those two are going to combine to form water, which would be considered neutral. So what is the net ionic equation for this reaction? So that means we need to remember what net ionic equation means. It means that we're going to split up everything that is aqueous and cross off the ones that are aqueous on both sides. So H plus aqueous and Cl minus aqueous, right? That dissociates. K plus aqueous and OH minus aqueous. That also dissociates. Does water dissociate? No, because it's not aqueous, it's a liquid. But the potassium chloride dissociates. And that means that I can look for these spectator ions. The spectator ions are the ones that are the same. They're aqueous on both sides and they cancel out. So what is left over is H plus aqueous plus OH minus aqueous yields H2O liquid. But then that makes sense, right? I know that an acid-base neutralization reaction neutralizes the acid and the base and therefore makes the neutral compound, which we know as water. So example 14.2 is just to do the same thing that we just did, but write the balanced chemical equation between HCl aqueous and calcium hydroxide. Calcium is a 2 plus ion. Hydroxide is a 1 minus ion. So pause the video here, try and get an answer for this, and then restart it and see how you did. So the formula for calcium hydroxide is CaOH2. And what will react? Well, the positive of one reacts with the negative of the other. So that's HOH or H2O. And then remember, the positive of one matches up with the negative of the other. But that's going to be calcium 2 plus and 1 minus chloride. So CaCl2, remember we have to crisscross the charges. And that's going to be aqueous also. And now if I need to balance it, I notice that there's 2 hydroxides over here, but there's only 1 hydroxide over here. I need to put a coefficient of 2 here, and then that means 2 hydrogen ions. I need to put a coefficient of 2 there.